Okay, so we are going to take a look at some of the word problems off of your problem set here. You'll notice there's a decent number of problems here. I'm not sure if we'll end up really doing all of them, but we'll see, because there's like 4 total pages. Our unit is work. What's our variable for work?
Capital W.
Capital W. What's the equation we had?
F times delta x.
Okay. You guys are going to let Michael carry everybody? It's like, Michael's going to... I'm putting the class on my shoulders. I'll get you to the finish line. Okay? Now, one of the things that we pointed out, when you talk about common experience, what's a force? Think real simple. If there's going to be a force, what's happening somewhere? Well, not necessarily. Just because there's a force doesn't mean there has to be movement. Because like if you go up to a wall that's solid, you can apply a force, but it may not move. But what's the idea? If there is a force present, what kind of interaction is somehow happening? 2 P words.
Push and pull.
Right. Something's either pulling or pushing on an object for some reason. So in order to do work, we have to have a force. Secondly, what did we kind of specifically mention has to be happening because there's a delta x in this equation?
The object has to move.
The object has to move. So again, going back to, like if I'm just pushing on a wall, I'm providing a force, but technically according to the physics definition of work, I am not doing any work because the wall's not moving. What was our unit for work? Simple one. Nickname?
Joule.
Joule. And what's the letter for the unit?
Capital J.
Capital J. Here's the trick one. I'm not going to ask you to do this, but without looking, anybody remember the MKS unit for joule? What's on the bottom? So, kilogram times meter squared over second squared. You will never ever have to remember that one, okay? But remember that that's where this all comes from if we talk about MKS units. Yeah, Connor. Yeah. Okay, so now we have to address how do you problem solve with this? And this can become a little complicated because you can apply forces in many different directions. So the idea of handling direction can become pretty complicated here. So we're going to kind of keep things simple. For our problems, we will have objects that are either just moving horizontally, and so they're not going up and down, or they will be moving vertically, and we won't be allowing them to move side to side. So let's start with an example we're just going to make up. Let's say I have an object that is 5 kilograms, which is about 11 pounds. So let's say it's like a box of books. And what I want to do, here's a table. What I would like to do is just lift it up so I can set it on the table. So all I'm worried about is lifting it this distance. And let's say that the height of the table let's say it's a pretty tall table. So let's say it's 1.5 meters. So what I want to do is calculate how much work do I do lifting the books up so that I can set them on the table. So when we're looking at this, what variable is the 5 kilograms? Remember, kilograms is always the same thing. It's mass. So over here we can say mass equals 5 kilograms. What does my 1.5 meters become?
Delta X.
That is our delta X. Okay, so now what we have to do is figure out what do we do for this F. Now, in looking at this problem, can anybody tell me how I'm going to figure out the F associated with lifting the books? Any thoughts?
Finding the displacement.
Well, we already got the displacement because we got the 1.5 meters here. But if I put 5 kilograms in here, that would be a bad move. That would be wrong because mass is not a force. But if I was lifting or lowering something, what force would I have to overcome?
Gravity.
Okay, it would be gravity. What do we call the force of gravity working on a mass?
Weight.
It's weight. So, I don't know if you guys remember this because this was a little bit ago. When we did forces, we talked about vertical problems where you were lifting and lowering things. And we said, I don't know, anybody remember this? No?
Was it positive and negative?
There were 2 arrows that were in the picture to lift or lower something. They were both F's, but this one was the weight. Anybody remember which subscript letter goes with this? Think logically. W, okay. Anybody remember what the subscript was that went with this one? It was A, okay. Anybody remember what the A stood for?
Acceleration.
No. Applied force. And in this case, where is the applied force coming from in this scenario?
Gravity.
No. What's happening in our situation?
Lifting it.
Okay. So where's the applied force coming from that's going to make these things go up?
You picking it up.
Yeah. Me interacting with it. Anybody remember how to calculate FW?
M times G.
M times G. So this equals M times G. And remember, we are very picky here when we do this, that up is a positive direction and down is a negative direction. So our G is going to be specifically negative 9.8 meters per second squared. Now, anybody got a calculator? All right. Tell me how much is the weight of my books here?
5 kilograms.
That's the mass. What's the weight going to be? And that's where we do the M times G. What do you get?
We got 49 kilograms.
49. Now it won't be kilograms because now it's a force. So what unit would go with it?
N.
And specifically what N? Capital N for newtons. And because it's down, it would be negative. Now, here is one thing that you're going to want to remember. And I think this will hold true for most of the problems that I'm going to give you. If you are lifting or lowering something at a constant velocity or a constant speed, what that means is that your FA and your FW are equal and opposite. You're not going to be picking up any more speed or losing any speed as you're being moved upward. You're just going to move at a steady rate. So I'm going to write this over here. Constant velocity means FA equals the opposite of FW. And remember, that is taking into account the fact that we are taking down to be a negative direction. So in this particular problem, I'm actually going to change colors with this, because when we are trying to figure out how much work am I doing when I lift this thing up, I specifically want the applied force here. And so I'm going to change this to highlight this is the force that's going to go over here. Now, based on what we just said, who can tell me how big that's going to be?
49.
It will be positive 49 newtons, because we said we're going to have this thing be lifted up at a steady rate. So now, to finish calculating the problem, all we need to do is take our 49 newtons, and I'm going to put the plus in there, multiply it by the 1.5 meters, okay? And what value do we get when we take 49 times 1.5?
73.5.
Positive 73.5. And what unit will now go on this? Because it's work.
NM?
We could put newtons times meters, and that would be accepted, but what's our nickname for work that we learned last time? Single letter? Okay, capital J for joules. Okay? So, this is the idea of a problem when you're lifting or lowering something up at constant velocity. The key thing that you need to find is the weight of the object, and then the applied force, which is the one that goes in here, is going to be equal but opposite to the weight, because all you're doing is balancing out the weight.
Are we just going over the previous problems from like 2 units back? We have like the sliding problem.
Well, now we can use, we had problems back a couple units ago where we had vertical and horizontal problems. We can now give you problems that sound like those, but they build on them, because the question is not going to be how much force do you need to apply to get something to move. Now the question will finish off by saying, if you actually push this thing this many meters, how much work did you do in the process of doing that? Now let's see.
Did you get it done? I'll copy it down.
All right, now I think we might have to make up some problems with this just for practice purposes. Okay? Everybody good with this? So we can,
Oh, we have
yeah. So I'm gonna erase this, and we're gonna create another situation. All right, and talk about it. Now this one, let's say, this time we're going to switch from a vertical scenario to a horizontal one. So the idea here is that we're going to try and push something across the floor. So let's say, do you guys remember your coefficient of friction, the whole 9 yards on that? We'll try and keep this easy to start with. Let's say you are going to be pushing on this. We're going to make up a number. Let's say it was 75 newtons. But then, what is usually present when you're trying to slide something across the surface? What other force?
Friction.
Friction. Okay? And which way does friction work with respect to the direction that the object is actually moving?
Opposite to
What?
opposite to which direction?
Opposite. So if I'm going to put an arrow for this, I would point it this direction, and I'm going to go ahead and say, I'm just making up numbers here. Keep it simple. Let's say it's 30 newtons, and because it's pointed the other way, what would I also be putting in front of it?
Negative.
Negative. And then let's say that we need to slide this thing a total of 5 meters. Okay? So the question is, how much work do we do? So our work is still going to be F times delta X, but this is where we're going to have a little bit of a discussion because there are multiple perspectives on this problem. Now, simplistically, what's our 5 meters? What's our variable for this? Levi? So which variable? That's our delta X. That's easy enough. Now here is where things can get a little picky. What would I call, because this is newtons, what variable is going to go with this? Just because it's newtons. Ben? It's F. So this is going to be an F. What about this negative 30 newtons?
F.
Also going to be an F. So what do we have to do that's a little bit more detailed now?
Give 75 F1, give negative 30 F2.
Okay, we need to like somehow distinguish them. Now, we'll start with one that I think's easy. What was this particular force here that I mentioned working against me trying to push this? Name of it? No? Friction. So guess what? We've used this before. What letter? It's F, so lowercase f. Okay? What F would this be if it's me pushing it? If this is going to be my FA. So here is where things can get a little picky. Because when I say, how much work is done, the answer to that question depends on which thing in this scenario are you focused on. And there are actually 3 different works we can talk about. There is, we could call it the applied work. There's the work done by friction. And then there is the idea of how much net work is actually done on the object. Okay? Now, who's responsible? Let's start with this. And I'm going to change this up a little bit. I'm going to call it, how much work do I do? So if I'm worried about that work, and I know this is my equation, I already know that this box is going to move 5 meters. But which F would go in this equation, this F times delta X, if I'm worried about how much work am I doing? Just me.
F of A.
It would be F of A. So for this, I would not worry about this, I would say I'm going to do 75 newtons, and I'm multiplying that by 5 meters. Anybody have that number? Who's got a calculator out?
375 joules.
Okay, so this would be 375 joules. Okay? Now, what if I said how much work does friction do? Which F would go here? Don't overthink it. What? Okay. That would be our frictional force. Now, that means we would do negative 30 newtons, and we'd still be multiplying that by 5 meters. Okay, the math is nice and clean here. What's our answer? Negative 30 times 5? Negative 150. And then what unit would go on it? Because it's work. Joules. Okay? Now, the last one here is what I'm going to call net work. And it's still delta X, but what F would belong here? This is kind of going back to our forces unit. Any thoughts? None? It would be the net force. Who remembers how to calculate the net force? There were actually two ways that we could do this depending on the problem. But when we had individual forces in a problem and we needed the net force, what did we do with all of them?
Combine them.
Okay, we combined them. That's where we have this sigma notation where we said the way that you calculate your net force is by adding all of your forces together. Now in this problem here, to calculate our net force, we only have two forces. Applied force and frictional force. And our applied force was 75 newtons, and our frictional force is negative 30 newtons. So how big is our net force?
45.
It's 45 newtons. And so to calculate the net force, we would come here and put 45 newtons here, and then we would have our 5 meters here. Okay? And what's our answer for how much net work is done?
225 joules.
225 joules. Okay. So now, here is where I'm going to see if you can kind of get the, because one question that I could ask is, what is the difference between these three different scenarios? Because they all have to do with work. The difference is, I don't know if who is the right word, because friction, you know, we'd have to imagine it's like a person. But the idea is, what is the force that we are focusing on doing the work that determines which answer is our correct one? Now, most of the time, if someone asks you, how much work did you do pushing that box across the floor? You would approach it from this perspective here, because you would say, look, I pushed with 75 newtons. And if someone says, yeah, but there were 30 newtons of friction, you know, we're only going to give you credit for 45, you know, you would be giving them the finger going, I pushed with 75. I want all the credit for the work that I did. So in that scenario, you would want to say, I want to use all 75 newtons to give me credit for my work. So you would say, I did 375 joules of work. Now the thing that will happen is that when somebody watches the box that you pushed, and we'll learn this down the road a little bit, one of the things somebody is going to say is, I don't see 375 joules of work out of this box in terms of how fast it's moving when it's gone this 5 meters. And the reason for that is this right here. That while you were pushing with 75 newtons, there was another thing acting against you. And it did work as well, but its work was negative. And because it was negative, that means that it worked against your work, the positive work that you did. So that when someone was looking at how much work does it look like was done on this box, they're not going to see all 375 of your joules. They're not going to see all of the negative 150 joules, but what they will see from outside of the situation is this net number of joules. And this would kind of be like if instead of we said this was friction, let's pretend that this was another person that was pushing at this negative 30 newtons. Then we would end up having this discussion about how much work did you do, how much work did the other person do, and then how much overall work got done on the box. Now, this can work. Everything, if there's a second force in this problem, it doesn't always have to work against you. You know, if we said, hey, there's this second person, what they're going to do is they're going to push, but they're going to push in the same direction that you do. Then both of you would end up saying, I did work, the other person did some work, but if their work was oriented in the same direction as yours, both of your works would add together to make even more overall work being done. So just keep in mind from this example here that work can be positive and it can be negative, depending on the primary thing that it depends on is what direction does the force that's acting on an object, what direction is it acting in? Okay, so these are the two basic kind of problems that you're going to encounter. Vertical one, lifting and lowering, or horizontal one, like sliding them across a surface. So what we're going to do here is, I think for today, let's see if we can look at one problem off of your worksheet today. Let's see. Let's just take a look at number 1. All right? And this is under the one that says work and power. Let's make sure we got plenty of time. Yeah. This ought to be good enough to set this one up. Okay, so if you read number 1, what kind of problem are we dealing with? Vertical or horizontal?
Vertical.
Okay, and what are we doing?
We need to find the exact weight of the turtle.
Okay, so the idea is we got the turtle here. It's all happy. And we need to lift the turtle up. Now, what pieces of information do they give us? What's one thing, Ben?
They give us the work, the distance, the mass of the turtle, and that's what they give us.
Okay, so what's the first thing you mentioned?
The work, which is 4.62 E4 joules.
Okay, hold on. 4.62 E4 joules. Okay, so that's one thing we have. What's the other? What's another thing that you mentioned?
The distance, which is 5.47 meters.
Okay, and technically, what variable would that be?
That would be delta x.
Okay, so that would be our delta x. Now, you mentioned a third one.
Mass.
Well, okay, now, read very carefully. Could you recognize why that we really can't use that?
Because they're trying to find the exact weight.
Right. So the idea is when they said because when you said mass, you were focusing on 800 kilograms. That's not the turtle's exact mass, is it?
No.
Because it says it's over that. So we know if we get an answer less than 800, we did something wrong. Okay? And this is a vertical problem. So what forces are we going to be playing with here that were in our picture?
Gravity.
Okay, and how would we put that in the picture? How would we put it into the picture? Okay, keep going.
So do a line up and down, 2 arrows.
Okay,
Like under the turtle, going down,
okay,
which would be weighted force, and then you have applied force, which is going up. And since we're lifting it out of the ocean and onto the boat, it's going to be applied force.
okay. So when we are looking at this, what we're really focused on is this guy here. Okay, so what can we do over here now?
We could find the force.
Okay, so we're going to use W equals F times delta X, and this is where I'm going to come back. You've already answered this, but when they mentioned this work, this was the work to actually get it up on the ship. So which F is in here initially? You had mentioned this a little earlier. Which F
The
is
applied
doing the
force.
lifting?
The applied force.
The applied force. So that's going to be our applied force. So now we can put numbers in here. Equals, we don't know what FA is. And we know that this is 5.47. Okay? Now what's the math we do? Because really, hopefully you go, oh, I got to get FA. What's the math we do?
Divide both sides by 5.47.
Okay. So this is going to be an F. We'll get the exact value on this.
The exact value is 8,446.1 newtons.
Okay, so we get 8.446 E3, and because it's an F, we got our newtons. Okay? Now, what is it that they ask for?
As for the exact weight of the turtle,
Okay, so let's stop there. Which thing in the picture is our exact weight? Or which thing in our picture is the weight?
the weighted force,
It's this guy here.
mm-hmm.
Which one did we just finish finding?
The applied force.
So we are up here. And technically, if I said be explicit and put a sign on this for me, which sign would we put here? You only got two options. What does that mean? Go ahead, say it, Andrew. Positive. There is a key phrase in here that allows us to go from here to answer this. What is it in the problem? And we had mentioned this earlier. There's a key 2-word phrase in there.
Constant velocity.
Constant velocity. What was special if we're lifting or lowering something at constant velocity? What does that mean about is the relationship between the FA and the FW?
They're the same.
They're the equal but opposite. So if I know this here, what does that mean this is going to have to be?
Negative 8.446 E3.
Okay? So this is our FW. Now, when we go to what is the exact mass, what equation are we going to bring into play?
N times G.
And so our FW we don't know what the mass is, and what does the G become?
9.8.
Technically,
Negative 9.8.
okay. So in order to solve,
Divide.
so when we take
861.8.
we get 861.8, and because it's a mass, what units would go on it?
Kilograms.
Kilograms. Okay. Do you get this? All right. I'm going to give you one additional one that you can work on today. Number 2. Okay? So you got 5 minutes here before you go. It's going to be, I'm not going to say exactly like this, but it's a vertical problem, and it does mention constant velocity. And so you could use the same principles that we did here about the FA and the FW being equal but opposite. See if you can work on that. Okay, so that'll be your one assignment for today.